Okay, now. Okay, guys, now we are just going to get started. I'm sure that all of you are so pretty much excited for this day. It's a beautiful day, guys, huh? Okay, now.
Yes, today
Oh,
is so beautiful.
how
Yes.
okay, Sean, are you getting ready for your presentation?
Oh, I will prepare for it.
Ah, okay.
Next.
Do you want to also talk about the Gibbs phenomena in MRI, mathematics of
Uh,
that?
let's see. I will do some researches probably
Ah,
about.
okay. Okay, no worries. Let me know anytime he's done. Next one is we have, I should say, Oliver coming, and I'm so excited for Minjae's presentation next Monday, and I'm
Yeah.
setting up some dates for Linda to see how possibly she can present, as long as she's in China and the connection of the internet is not a stable one. I'm thinking of one solution for it, and let's see what do I end up with. Okay, guys, now let's get back to the things which we did yesterday. Now today we are just gonna prove and drive two identities, which is extremely important, and you are gonna use that a lot, specifically when we just go to the inverse of trigonometric function. The starting point of it is these two identities that we drive them yesterday. It was so simple to find them. These identities were derived by using, I should say, the sum of two angles for a cosine trigonometric ratio. When those two angles were equal, then we ended up with these two identities. It was the result of the thing that we derived it yesterday. And also at the same time, we noticed that how we can use them in the power reduction techniques that where is that? Yes, that's it. And we noticed that how we can use them successively. For example, on the example which we had yesterday, we noticed that how we can use them successively in order to reduce the powers of the trigonometric ratios and expressions from the high powers, reduce them successively to the power 1, which we noticed that what we did yesterday, and we were able to express this identity, not identity, that's the identity in a sense that we created, but we saw that how we can just use those two identities as a power reduction technique for successive reduction of the powers of, let's say, sine to the power 4 of the x. And we saw that this one was reduced to an expression which you see that the cosine of to the right side has the power 1. And that's why we call that a power reduction technique, because you start with the high power, but you end up to power 1. And that's the beauty of those two identities. We're going to just spend some more time today on it and do some practices there. But before that, I introduce two more identities. Then we just get back to some, I should say, more practices specifically for the power reduction technique. Okay, but before I just start the new lesson, two things to mention. I'm going to ask you, does everyone have these two identities written in front of you? Jason and Oliver, Linda, anybody has, and David, and also Brian. Does anybody have these two identities written right now?
Yes.
Yes? Okay. Nice.
Yes.
Now I'm just gonna start to continue from these two ones to drive two very important identities. Okay, the first one that we just want to attempt today, it's gonna be this. I'm just gonna start from this identity. Cosine squared. Do you see this color? Oh no, do I have to change my color?
You can change color.
Color? Oh, okay, it's not a good color. Let me do that. Okay, let me choose this one. Okay. I'm going to start with this identity. Oh, give me 1 second. I need to just go to find my ruler. Without the ruler, it seems that I cannot work. Give me a second. Okay. Now I have my ruler back. Let's get going. Okay. Yesterday, the thing that we discussed and we thought in one of those identities was this one. We said that the cosine squared of x as an argument was essentially written as a basic of a power reduction identity, which it was 1. Linda, is it a good color? Is it better than the other one?
Yes.
Okay. We saw that it becomes 1 plus cosine of 2x divided by 2. That was the identity that we used yesterday as one of the techniques for the power reduction. So I call that successive power reduction. It means that you are going to use these formulas iteratively and successively to reduce the powers of the higher powers of the trigonometric function. We said that when we have this, simply I can just come here, express that in terms of the cosine of the x, because my plan is that to write the half angle identity. In order to find this, I'm just going to do what? I'm just going to find the cosine itself, not the square root of it. Then it means that I can take the square root from both sides, and I get cosine of the x should be equal to this expression. Becomes 1 plus cosine of 2x divided by 2. Correct? Is this correct or no?
Yes.
Who says yes?
Me.
Linda says yes. How about the others? This is correct in a sense if I put plus and minus before the square root. And the interpretation of the plus or minus, it's in a sense that if the x is chosen as a counterclockwise on the unit circle, it refers to the plus, or x if this is chosen as a clockwise on the unit circle, which we talked about that, I should say, maybe a couple of weeks before, then that's going to be the minus sign in front of, I should say, the square root. Then we have two answers depending on how you decide to rotate along the unit circle in your, I should say, your setup for the trigonometric, I should say, the representation. And that's very important, plus or minus. And now the thing which I'm just going to do, I'm just going to try to express this identity which I have here just in terms of 1, I should say, with the power 1. And how am I going to do that? Because the plan is that I'm going to write, guys, the strategy for this is that. That's the main goal which I have. I'm going to express the cosine of 2x, which is represented inside the square root on the right side, to represent that only by an argument which has coefficient 1. Then by doing that, you will see that I'm going to get to the left side half of this angle. That's the plan, and we call those identities half angle identities, and they prove very useful when you just want to just, yes. Linda, you said something? Linda?
Yes.
You said something?
No.
Oh, okay. Then I continue. Then in order to do that, at this stage, which is, I should say, we are just working on it, I simply write this one, that 2x, imagine if it's going to be represented by a change of variable, let's say, by a change of variable, let's call that, for example, it's so hard to choose. Let's choose it alpha. Okay. I'm going to choose this one alpha. Then I see whatever I have inside the square root is now is going, if this is 2x, I'm going to represent it by the alpha. But what about the x over here? Because if you look at this identity, you will see that the true nature of my variable, the essence of my variable in this identity is represented by x. And you can see that, you can see this here. This is x, this is x. Then it means that, for example, you are representing, for example, this one. For example, imagine x is supposed to be, for example, Brian. Brian, are you there? For example, on the left side, we have Brian. On the right side, we have true Brian. If I change 2 times after Brian to, let's say, for example, Mingje, then definitely on the left side, I have to change Brian to Mingje. I cannot have 2 Mingje there, 1 Brian there, because x is the essence of your variable. It has to be consistent. Then in a sense, if cosine of 2x, because 2x, you change the variable to alpha, then x on the left side should be represented by what? Then alpha is x becomes what? Alpha over 2. Oh, I hope that you see that color. I forgot I should not use the colorful, I should say writing. I hope that you see that this is 2x equal to alpha, and this is x. Then if you divide both sides by 2, you get x equals to alpha over 2. Okay. And now what's going to happen now? I'm going to rewrite the expression which I have written with this format. I'm just going to write this one just only by changing the x to the alpha. What I'm going to have here, I'm going to have the cosine of x is going to be written as alpha over 2 should be equal to what? One plus cosine of, and now I have 2x. I changed the variable 2x with another variable. That's what they call that change of the variable. And it doesn't make a difference because you know that you can, your variable, you can name it anything. You can name the variable x to z, provided that you are consistent by changing the variables anywhere from x to anything which you decided to be. Then it becomes cosine of 2x becomes alpha divided by 2. Still, I do not forget that I should have plus and minus before my expression because it's the way which represents if x is chosen counterclockwise or fx is chosen clockwise. And that's how it is very important. Okay, and now welcome to this very important identities. We call that guy the half angle identity, which is represented as this one. Cosine of alpha over 2 is plus or minus square root of 1 plus cosine alpha divided by 2. They call that half angle identity. Please make sure that you write it exactly by the way which is written. And now at the end, you can change alpha back to x. You can say cosine x over 2 equals plus or minus square root of 1 plus cosine x divided by 2. Okay, that's the first identity that we have it right now. Any questions, guys?
No question.
No questions. Glad to hear. Okay. Shall I take the page over? Okay, now I'm gonna do the same thing, the same procedure. It's a little bit hot in here. For the other identity, which we had what? We expressed something for the sine squared of the alpha. I'm going to write it for the x now. We had what? We had sine of, I should say, sine squared of x was equal to 1 minus cosine of 2x divided by 2. I'm going to do the same thing as I did before. I'm going to express the identity based on power 1. Then I'm going to get the sine x should equal to, taking the square root from both sides, then it turns to be 1 minus cosine of 2x divided by 2. I'm going to take the same, but plus or minus, which I was going to almost forgot. Then I change 2x as to become the alpha. Then you see that x becomes alpha over 2. Then as a result, I'm going to end up with that sine alpha over 2, which is half angle, is going to be written as this. Becomes 1 minus cosine of alpha divided by 2, and you see that I have plus and minus sign there. It is going to be our second identity representing half angle for the sine ratio. Beautiful stuff, guys. Oh my God, I can't have enough of them. I like them. That's the sine alpha over 2, then it's expressed by that. Any questions, guys? No questions?
No question.
Okay.
No question.
Awesome. And now, the plan now, guys, is that I'm just going to give you this assignment to work on it now before I do that for you. Now, I just want to ask you, please, as an exercise, I'm going to do that myself, but before that, I just want to see what's the result that you get, to find the same expression as the tangent of alpha over 2. Find the same expression for this one. Please give it a try yourself. You have a couple of minutes, 2 or 3 minutes. Please give some time to see that if you can derive the same expressions for half angle for the tangent. Give it 2 minutes. I'm sure you can do that. Yeah, good luck. Anyone is done now? Who is done? No one yet? Hello? Anyone is young, guys? No one yet? Mingzhe, Sean?
I'm done.
You're done. Fantastic.
Yeah.
Fantastic. What expression did you got, Mingzhe?
Tangent alpha over 2 is plus or minus root 1 minus cosine alpha over 1 plus cosine alpha.
Fantastic. Fantastic. Great job. Look at
Thank
that,
you.
guys. In order to find the tangent of the half angle, we know the definition of the tangent of, we have seen the definition of a tangent of a ratio. We know that the tangent of x, essentially what we have learned, it becomes the sine of x, which is going to be divided by the cosine of the x. And now that's the thing. We just want to find the tangent of the alpha over 2. It's essentially like that. You have to say that the tangent of alpha over 2, it's essentially what? It's essentially a simple trigonometric ratio. What is that going to be, Brian? Sine alpha over 2 divided by cosine of alpha divided by 2. Okay, but the problem is that, not the problem, I should say our advantage is that we know about these two, the numerator and denominator. Why? Because we've got these ones here. We said that, okay, the sine of the alpha over 2 is this expression. Then the thing which I'm going to do is this. I'm coming here to replace it with this one. Instead of writing the sine of alpha plus 2, I'm going to write its equivalent term, which is going to be this. Let me change my color. For the sine of alpha over 2, I'm going to write this, which is 1 minus cosine of alpha divided by 2, and I have plus or minus sign there. And also for the cosine of alpha over 2, I have the same thing. Everyone can see that? Becomes what? Becomes 1. For the cosine it was 1 plus cosine of alpha divided by 2 plus or minus back there. Okay, now it's going to be very easy that you can just mostly summarize this one by, I should say, we can just remove, I should say, 2 from the denominators from both sides and keep the square root from both terms. Then at the end, you end up with this expression that the tangent, I think I need to write it on the other side of the page. So far, so good. Everyone has written what I've written here. Can I just flip the page over? Linda, you have written it?
Yes, teacher.
Okay, then I'm going back to the other page. If no one else complains, it means that everyone is up to page 10. Then we get what? We get the tangent of alpha divided by 2 should be equal to what? Should be equal to only one simple expression, which is going to be the plus or minus the square root of this one, which becomes 1 minus I think it becomes cosine. That's right. 1 minus cosine of the alpha divided by 1 plus cosine of the alpha, and at the same time as before we have plus or minus sign back there, which is going to be the half angle identity for the tangent of the alpha. We call that half angle identity. And plus or minus sign, again, that depends on how you just segment your alpha on the unit circle and which quadrant you end up with. Okay. Any questions, guys?
No question.
No questions. Now, guys, I'm just going to continue from this and derive an expression for the tangent of the half alpha in a case that we do not have it expressed by the radicals. I mean by rationalizing it. Then I'm just going to do that for you. But in order to rationalize the expression, I mean freeing it from the radicals, I'm going to do what? I'm just going to multiply both sides to the conjugate of the denominator. The conjugate of the denominator becomes what? 1 minus cosine of the alpha. Huh? That's right. It means that you change the plus to minus, it becomes a conjugate. Then what's going to happen now then? I'm just going to write it here like that. We are going to draw a very important identity, which is almost everywhere. We're going to get it like that. We're going to get tangent of alpha over 2 should equal to what? Square root. For this one, I have 1 minus cosine alpha, 1 plus cosine alpha, but I multiply that to both sides, to the numerator and denominator, by the conjugate of the denominator, which becomes what? Which becomes 1 minus cosine of the alpha. Look at that. I have 1 plus cosine alpha, and I have 1 minus cosine alpha. It's plus, it's minus. That's why you call these two expressions are conjugate of each other. 1 plus cosine, 1 minus cosine. The only difference is the minus between them. The sign is different. Or if this is minus, the conjugate becomes plus. And you know that if I did the same thing, I have to do the same thing for the numerator in order to preserve this expression, because the same thing, 1 over minus cosine alpha, the old expression which is written in pink, it essentially becomes 1, and it seems as if I have no impact on my main ratio here. Okay, now, then what's going to happen now then? Still, I know that I have plus or minus before that. What's going to happen there? I'm just going to write the simplified format of this. I'm just going to write, it becomes the square root of what? For the denominator, it becomes very easy. You have seen this identity. 1 plus cosine alpha multiplied to 1 minus cosine alpha. You have seen this conjugate identity, which turns out to be 1, the first term to the power 2, minus the second term to the power 2, which is the second term is cosine, to power 2 becomes cosine squared of the alpha. That's right. That's the thing which we got for this one here. But also, at the same time, what's going to happen here? We're going to end up here with 1 minus cosine alpha times to 1 minus cosine alpha, which both are the same thing. Then as a result, it becomes 1 minus cosine alpha squared. Correct? Still, I have plus or minus sign depending on where in the quadrant you end up there. Then it ends up to, any questions, guys, so far? Everything is clear up to now? Hello?
Yes.
Linda, Mingji, Brian, Oliver?
No question, teacher.
Everything is fine. Oliver, Brian?
Yes, yes.
Fantastic. Then now, guys, look at this one here. We ended up at a place that we are going to see so much excitement. First of all, look at the denominator of this expression. We have 1 minus cosine squared of the alpha. It is going to be equivalent to what? Mingje?
Sorry, what's your question?
I have here 1 minus cosine squared of the alpha.
Yeah.
What does it remind you of?
Sine square alpha.
Fantastic. I'm just going to write this one. Then it becomes essentially sine squared of the alpha. Linda, Brian, Oliver, for everyone, is this clear?
Yes.
That's right. Then as a result, I have what? I have this expression like that. I have the square root of one minus cosine alpha to the power 2. And here I have, based on the identity, we call that the fundamental identity. That's the first identity we started with. Then it's going to become sine squared of alpha. I know that I have plus or minus sign there, depending on where in the quadrant you are, that the tangent is going to be plus or minus. Then now, guys, look at this one. The problem which I have here right now is essentially like this. Let me go to the other page. I'm going to go back to this. We have this identity from before that if you have, for example, the square root of a to the power 2, yes, it becomes essentially what? It becomes essentially the absolute value of the a. That's what you take out when the exponent, the power of your argument is 2, which is exactly the same thing as the square root. Then when you just remove it from, I should say, the square root, then you have to take it out with an absolute value. Why? Because imagine that. And what is this reason for it? Imagine this example. I have, for example, the square root of minus 2 to the power 2. What is the result? You know the result is going to be 2. That's right. And a is minus 1, minus 2. You cannot take minus 2 outside. You know that it has to be plus 2, because what you do first is that you impact 2 to the power minus 2, which becomes 4. Then the square root of 4 becomes 2. But then if you want to follow this identity, you know that you cannot take a outside if a is negative, because the result of this square root is not going to be something negative. Then that's why you put minus 2 in case if it is minus, then it becomes the absolute value of minus 2 becomes plus 2, which is the same result. Then that's a kind of a cautionary step to put the absolute sign of your argument to avoid taking something negative directly outside from the square root, because we know that in math, the result of the square root of an argument can never be negative. That's why we put the absolute value there. Then as a result, previously, what did I end up with? For the tangent of, I'm going to rewrite it again. For the tangent of alpha over 2, I got this expression. I'm going to rewrite this. We got the tangent of alpha over 2 was what? Was the square root of this expression. The expression is this: 1 minus cosine alpha to the power 2, and it's going to be sine squared of alpha. Correct? The same thing, look at this identity, but now we have a rational expression because that's numerator and denominator, but all follows the same rule. We have 2 and we have 2 here. The powers are both 2, and that's the square root. Then it means that we can just take them out like the identity which I showed out to you. Correct? That means that becomes what? Becomes 1 minus cosine alpha. You remove power 2. Remember this identity which we learned. And now you have sine alpha at the back, but you are very careful to represent that inside the absolute value to make sure that whatever you get as a result of operating is square roots is going to be something positive at the end. And of course, also, you still know that we carry this plus or minus sign from before. Then, to wrap up this identity, we derive this, that the final word is that the tangent of alpha over 2 is equal to plus or minus, depending on plus and minus depends on where quadrant you are ending up with, over what? The absolute value of 1 minus cosine alpha divided by sine alpha. Let me highlight this around a circle, because this identity, guys, it's a gold one. It's a very important identity. Please make sure that you write it as what I have written. And if you have any questions, please ask me now. Okay, guys, does it make sense? Do you have any question or any concern? Guys? Hello?
Hi.
Any questions, guys?
No question.
No questions? Okay. Then that's the thing which we drive it right now here. Okay, then now you see that, guys, we have two expressions for the tangent of the alpha over 2 for half angle. The one which we simply derive by dividing this sine alpha over 2 divided by the cosine of the alpha over 2, which is going to be this expression. Then we can just rationalize it to end up with this very important expression. Okay, then we have two expressions for the tangent of alpha over 2. Okay, I'm just going to give you one example to you derive something for me. Let me see what's going to happen now. If you... Okay, guys, please go back to, what time is it now, by the way?
9:51.
Oh, okay, that's good. We have 10 minutes at least. Let's catch up with 15 minutes before we go for the break. Guys, if everyone is tired, please stand up from your chair. I'm gonna do that myself. I stood up from my chair. I'm stretching my muscles. You do that the same thing. Don't get exhausted because we are gonna do something important. I'm just gonna stand up from my chair, walk for 2 seconds, come back to not to be exhausted. You please do the same thing. Just stand up and walk. Okay, I'm back. I did my exercise. Okay, now, but I have one question for you guys to do.
Okay.
Did you do the same thing, Linda?
No.
No, you didn't
No.
stand up from your chair to stretch your muscles? Okay, no worries. Okay, guys, now listen. I'm gonna ask you this question. Please go back to this part of your notes. Which part of your notes is that gonna be? This is gonna be here. That we said that the tangent of alpha over 2 is gonna be plus or minus square root of 1 minus cosine alpha divided by 1 plus cosine alpha. Correct? Please go back to there. And now, look at this. The thing which I did was this. I looked at 1 plus cosine alpha because the plan was to rationalize. I'm just going to write it here, rationalize. Rationalization. Wow, such a huge word. And the purpose was that, the plan was that, the old goal which I had, the radicals, you see, it is not always very convenient to work with because it's like the chain, the shackle, it imprisons the argument under the radicals. Then the plan always is that to get rid of it, to free whatever we have underneath of a radical. And one of the best strategies was this, that I came here to decide to multiply both numerator and denominator into the conjugate of the denominator, which was 1 minus cosine alpha. Then I ended up to this expression, that the tangent of alpha over 2 becomes 1 minus cosine alpha divided by sine alpha in absolute value. Correct? And now, the same thing which we want to do right now here is this. We are going to do this one. We say that, okay, we essentially, what do we do is that instead of multiplying to the conjugate of the denominator, I'm going to do this by multiplying that to the conjugate of the numerator. The conjugate of the numerator is what? What does that mean, Jay?
Can you repeat your question?
What is the conjugate of the numerator?
Sine square alpha.
No, I didn't mean that. We have 1 minus cosine alpha. Its conjugate becomes 1 plus cosine alpha. You always change the sign. In order to rationalize your expression. You see, what did I do? I came here to multiply both signs, numerator and denominator, by the conjugate of the denominator. The denominator is 1 plus cosine alpha. Its conjugate becomes 1 minus cosine alpha.
Yeah.
But now, my question to you all is that you have 5 minutes to do this. I say now, redo the same work, but by rationalizing your expression by the conjugate of the numerator. What do I mean? I'm going to write that here for you. We had what? We had the tangent of alpha over 2 as what? As plus or minus of this one. That's what Mingjie also told me. Correct, Mingjie? You said that it's gonna be plus or minus 1 minus cosine alpha over 1 plus cosine alpha. That's correct, Mingjie? That's what you derived initially, huh?
Yeah.
And that's the first, I should say, identity which we derived for tangent of half of angle. Now, we said we have this square root, this radical. We want to get rid of it. And what to do? I'm going to come here and I say, okay, now I'm going to multiply both sides to this expression. Previously, I multiplied everything to 1 minus cosine alpha over 1 minus cosine alpha. I'm gonna 1 plus cosine alpha times 1 plus cosine alpha. You see, previously it was, what I did was 1 minus cosine alpha. Now I'm doing that with 1 plus cosine alpha. And now, guys, I want you, please, I give you 5 minutes to continue with this and write an identity which again represents the tangent of half angle with a different, I should say, expression. Yes, Sean?
Yes, yes.
Yeah, please go on. Go on, man. Please, everyone, continue. Linda, did you got what's going to happen?
Mm,
Continue with this. Multiply these things together, and as I did before, see how far you can go. Multiply this to this, multiply this to this, and simplify that. Okay?
okay.
Awesome. Good luck. I give you maybe 3 minutes should be fine then. Then we have gonna have lots of break. Beautiful day, huh? Guys, are you done?
Yes.
Yes? What is
Yes.
your answer? What is your answer, Linda?
Tangent 2 of x.
Say that again.
Tangent. Mm,
Okay. But Linda, no worries. Tell me if the thing which I'm gonna do is correct or not. Okay.
okay.
Okay. Is it the first thing which you did? You came here, you said that, okay, you're gonna take the square root because it's gonna stay there. And when you multiply these ones together, you ended up with this one. You multiplied the numerator to each other first, correct? Then you said 1 minus cosine alpha times 1 plus cosine alpha. Linda becomes 1 minus cosine squared of alpha, correct?
Yes.
That's what you did. And also, you multiplied, Linda, 1 plus cosine alpha to 1 plus cosine alpha, correct, Linda?
Yes.
What it becomes? Becomes 1 plus cosine alpha, because both of them are exactly the same thing. When you multiply that, you end up with this expression, right?
Yes.
Awesome. Then you didn't forget, Linda, to put plus or minus back, yes?
Yeah.
Awesome. It seems that you have done a great job, if that's the case. And now how about this time, Linda? You have this one, 1 minus cosine squared of alpha. Linda, isn't like, for example, you know that cosine squared of alpha? You know this one, huh? You know that cosine squared of alpha plus sine squared of alpha equals to 1, right?
Yes.
Then 1 minus cosine squared of alpha becomes what? You keep 1 there, take cosine squared to the other side, you have sinus squared, huh? That's right, Linda.
Yes.
And also you have this one, 1 plus cosine squared cosine alpha, everything is squared. I didn't change the one at the denominator.
Yes.
And what did happen, Linda, at the end? You say, okay, you say this is squared, this is squared, then the squared bracket. Then you say that based on the identity that you learned, you put the absolute value term and you remove everything without the power. You remove this one without power 2. Becomes what?
Sine.
Alpha.
Yes.
And also you remove the denominator without the power, which is 1 plus.
Cosine alpha.
Fantastic. Oh my God. Impressive, Linda. Thanks. And did I forget anything, Linda? Plus and minus before. Huh?
Yes.
It's always I forget it myself. It's very inconvenient, but I did it now. Then what do I end up with is this, that the tangent of alpha over 2 becomes also this.
Yes.
Right, Linda? You did the same thing? You followed the same thing?
Yes, this is my answer.
Fantastic, Linda. I'm so impressed. Fantastic. Fantastic, Linda. Clapping my hands for you. Brilliant. Thanks. Guys, today was a very productive day. Why? Because, oh my God, I lost counting of the identities which we derived. We derived half angle identities and 3 for the tangent identities. Then remember, guys, for the tangent half angle, we have 3 identities. We're now gonna take the break because it was a very productive, I should say, half period, and it kept us quite busy and exhausted. Then we take a break. We come back. This is now 10:07. We come back by 10:15. 22. Is it good?
Yes.
We take 16 minutes
Yes.
break. Even one more minute, more minutes than usual then. And Sean, in the meantime, you think of the Gibbs phenomena for the MRI.
All right.
Yeah, you were supposed to do that for the physics. We changed the topic to microscopy. The MRI was left behind. And now that's a good chance you can catch up with the physics and also the math both at the same time.
Gibbs phenomenon.
That's right. And anybody else, if is interested, they can do that. I'm going to put that as something on the Schoology website. Anyone who's interested can do that.
Okay.
And yeah, guys, let's take a 16 minutes break. I see you back all in 10:23. Enjoy your break, guys. See you soon then. Hello, guys. Sorry, I was late. Am I late? Anybody is back?
Yes.
Fantastic, fantastic. We had a very productive day by writing all these identities so far. Okay, now. Okay. With the time which is remaining, we are going to see some applications that why did we try to learn these half-angle identities and what they are good for. In order to see a very small, I should say, applications of these ones, why they can possibly be good, we just have two examples. Tomorrow we have more rigorous and more advanced examples now, but today we have some very minor ones. I just want you, please, to, I did this for the first one myself. For example, we talk about, for example, the sign. I write as an example. I say that, for example, evaluate the sign of 15 degrees. Sorry, guys. Okay. The sign of 15 degrees. Guys, I think I'm dying. Okay, now, the sign of 15 degrees. It's essentially, we see that it's very relevant to, let's say, if we can write it as what? As a sine of 30/2. That's correct? Now, we see that, for example, when we are looking for the exact value of the sine of 15 degrees, we have no connection whatsoever between 15 degrees, which is on the first quadrant of our unit circle, with any reference angles which we have known so far. How many reference angles do we have, Brian? Brian?
Yeah.
Okay, maybe. How many reference angles do we have so far?
I can't see it clearly.
How about now? No, I mean,
No.
my question is something different. I say that how many reference angles have we learned so far?
Angles. What is reference angles?
Oh, I mean, for example, the angles which we know everything about them in terms of its trigonometry and geometry. We know about triangles, everything. 30, 45, and 60.
This.
Oh, you got it, huh? You remembered it.
Yeah.
That's right.
Yeah.
Then we see that when we talk about the angles, we always, our strategy in trigonometry is that find a way to find any kind of connections with them. Because as long as we establish that connection between the angle which is represented by those reference angles, which is either 30, 45, or 60, we can find all information about them. Now, 15 degrees, it's in a very clear way is connected to 30 degrees because you saw that 50 is equal to 30 divided by 2. Huh? And that's how I connected 50 with one reference angle. Huh? Then as a result, how can I find this out? I mean, sine of 30/2 is the sine of 15, which I'm looking for. But I know that this unique thing in my, I should say, denominator, that I have 2 at the denominator, which it reminds you of what? It reminds you of this, I should say, half angle identity, which we had this one here. Remember, sine of α/2 equals to plus or minus square root of 1 minus cosine alpha divided by 2, correct? And now then as a result, I'm going to rewrite this one here again. I say that I know this identity, that sine of x over 2, it's what? The sine of x over 2 is essentially the square root of 1 minus cosine of the x divided by 2 plus or minus d4. Okay, now at this stage, what are we going to do now is that I'm just going to replace, just find the valuations like this. I'm just going to exactly do the same thing. I say the sine of 30 over 2, which is essentially the thing which I'm looking for, because it becomes 50, becomes what? Becomes the square root of what? What, Mingzhe?
1 minus cosine 15 degrees.
No, look
Oh,
at this
30
identity.
degrees.
That's right. Look, the beauty of this identity is that you represent half angle with a complete angle.
Yeah.
You see, I have on the left side, I have half angle because I divided my angle by 2. That's why I call it half angle. I represent it on the right side by a complete angle. Then if I have 30 over 2, it's going to be complete angle 30. And why it is beneficial? Because I know everything about 30 now. That's right.
Yes.
What is cosine of 30?
Root 3 over 2.
That's right. I'm going to write it here that the cosine of 30 is root 3 over 2. And you see, by using this identity, now I have the power to express that 15 degrees in terms of that. It becomes what? Becomes the square root of 1 minus square root of 3 over 2 divided by 2, which you take, I should say, the common denominator from this, then it becomes, let's say, and 2 over 2, it becomes gone, then becomes this square root of 2 minus square root of 3 divided by 2, which is going to be the last resultant. Then you see that when I use this half angle, which it provides a way for me to express my half angle in terms of, I should say, a complete angle over there, then as a result, what do I get? I get an expression that on the right side, I have all complete knowledge about that. I know what is cosine of 30. The cosine of 30 is what? Is the square root of 3 over 2. Then by doing some, I should say, algebraic manipulation, I get the common denominator of this becomes 2. I have the square root, 2 minus the square root of 3, and I have, I should say, 2 at the denominator. And now I know that it expresses the sine of 15 degree, which I know now that the sine of 15 degrees becomes this. But before knowing that identity, the half angle, it was impossible for me to find any evaluation with respect to the sine of 15 degrees then. Was it clear for everyone? Any questions, guys?
No question.
How about Linda, Brian, Oliver, Sean?
No question, teacher.
You got it, Linda?
Yes.
Awesome. Guys, now if you found it, please, before the end today, I'm going to ask you please to do the same thing for the cosine and the tangent of 15 degrees then. Use all the things which we learned today to write what is the cosine of 15 degrees and what is the tangent of 15 degrees then. Yeah, please give it a try yourself. Then I solve it to make sure that we are all at the same page. Okay,
Okay.
awesome. Give it a try. Then we should be done today. We do more advanced thing tomorrow. Okay, guys, please let me know whenever you're done. Hadi buyurun. Okay, are you done? Guys,
Yes, teacher.
Linda, are you done?
Yes.
Fantastic, fantastic. What is your answer for cosine 15?
Wait, teacher.
Huh?
Mm,
I know it's so hard sometimes to even to read the answers because it becomes so much square brackets inside. No worries. But let me know if that's the same thing which you have done. Cosine 15 degrees becomes what?
is
Becomes essentially, yes. Yes, Linda.
0. Wait, is 0.64.
Ah, okay, you simplified that. I do not know if that's correct or wrong because I didn't go that much into further to details, but let's see if that's the thing. Maybe you're right because I didn't just put that in calculator to see what is the end result. I was a little bit lazy. I didn't go that far. Okay, and now let's see if Linda is correct or not. Okay, I know that the cosine of 15 degrees, Mingje, is what? Is essentially the cosine of 30 over 2, which is essentially, that's the thing which we learned before, which becomes the cosine becomes 1 plus cosine of 30 over 2, right? But now look at this. I use this identity which we learned. What was that identity that we learned before was this, that the cosine of half angle can be represented by this identity as a cosine of the full angle. You see, that's the beauty. You start with half angle, you end up with the full angle. That's right. And that's what we did before. And now, the thing which I do is this. I'm coming to write the same expression, but I know the cosine of 30 degrees. Means we said that before. It's what? What was that, Mingje? 1 plus?
Root 3 over 2.
That's right. And all goes to the 2. Then at the end, if you simplify that, you end up with this result, that it becomes what? You can keep 2 here. You have 1 full, I should say, square root. It becomes 2 here plus square root of 3. And you see that these two examples are so similar. The sine of 15 degrees was the square root of 2 minus the square root of 3 over 2. But the cosine of the same angle, it's almost the same, but there is a plus sign there. It becomes the square root of 2 plus the square root of 3 divided by 2. Yes? Any questions, guys?
No question.
No questions. Awesome. Thanks, Mingje. Linda, that was the same thing which you did, huh?
Yeah.
Awesome. How is, I should say, Brian and Oliver and Sean doing? They're so quiet today. Brian, how's it going, man?
Just not bad.
Not bad. Do you have any questions?
No.
No? Are you doing cool, great?
Huh?
Are you doing great? That everything is fine?
Yeah, it was not fine, but now it's fine.
Ah, okay. I'm so glad to hear it. But
Yeah.
Brian, if you miss any sessions or even if you happen to be late on any classes and you miss some parts of the lesson, always remember, I hope that you have noticed that I record all videos, all the lectures, and at the end of each day, you receive a note from me that I provide the link of these 2 days lectures then. You get those notifications?
Yeah.
Yeah?
Yeah,
In case that's
I
good.
saw that. Yeah.
Oh, awesome.
Every
In
day I
case,
see that.
oh,
Yeah.
fantastic. In case if you have any question, if you have any clarification needed to review the lectures, it's always on the YouTube then.
Yeah.
And you can always send questions to me, email me your questions, post that on the Schoology, but make sure that you are you are not behind. You are on top of the courses. Okay.
Okay.
Fantastic, fantastic. Okay, now we are going to the final thing for today, which is the tangent of 15 degrees. Who's done with it?
I'm done.
You are done. Fantastic, fantastic. Let me, how much did you get, Mingje?
2 minus root 3.
I think you should be right. Let me catch up with my formula. What was the formula which I got for the tangent? I forgot to, the tangent. Oh, here. Did you use this one?
Uh,
1 minus tangent of half alpha. It's 1 minus cosine alpha divided
oh
by
yeah,
sine.
yeah. I used this one.
Oh, fantastic. I was looking for it. I don't know why I couldn't remember it myself. Sometimes I have to stick to my own notes. Okay. Now, the question, oh, where is that note itself? Here. The tangent of 15 degrees, guys, I know that it can be written as the tangent of 30 divided by 2. I'm just going to do what? I'm going to represent the half angle by the full angle itself, which I'm using this identity that we derived it before to go to the break. The tangent of alpha is alpha divided by 2 is equal 1 minus cosine alpha over sine alpha. Okay, let's see. It becomes then the absolute value of 1 minus cosine of 30. Look at this. This is a full angle in contrast to half of the angle which we have there. And that's beauty of this identity divided by the sine 30 degrees then. Okay. And now what is, I'm just going to put the values because as Brian said, we know that the 30 degrees, it's a reference angle. It means that we know all things about that. It becomes what? Becomes 1 minus the cosine of 30 is the square root of 3 over 2. That's correct? And the sine of 30 is 1 over 2. Then at the end, if you simplify that, you end up with 2 minus square root of 3. Because you take the common denominator first, it becomes 2 minus the square root of 3, and you have 2 multiplied to that from the denominator. Then you end up with this expression. Is it clear for everyone?
Mm.
Yes.
Thanks, Mingjae. How about Brian?
Yeah.
Are you sure, Brian?
Yeah, I'm sure.
You can reproduce the same thing, huh?
Mm.
Yes?
Yeah.
Fantastic. How about you, Linda?
Yes, teacher, no question.
You are totally fine, huh?
Yes.
Awesome. How about you, Oliver? Oliver was so quiet today.
I'm good. I'm good.
You are good? No questions, Oliver?
No.
Fantastic. You are getting ready for your this coming Friday?
Yes, almost.
Almost. Great. I can't wait to see your presentation on that topic then. Keep a good job then. Thanks, Oliver. How about you, Sean? Any questions?
No, not at all.
Awesome.
Yeah.
Now, guys, if nobody has a question, I have to wrap up the day today and say congratulations, guys. We did a phenomenal job today. It was a very productive day. We learned lots of cool identities, which these identities, they were called half angle identities that enables you express the half angle with the full angle on the other side. And that's what is called half angle identities. We covered that, 1 for sine, 1 for cosine, and 3 for tangent of half angle then tomorrow when we start, we have more advanced and complicated stuff regarding this. But by using these examples of 15 degrees, I wanted to draw your attention to the fact that these half angle identities sometimes numerically can help you to find the exact values of some angles. For example, for 15 degrees, we all got exact values, which you see that we got it here. And that was essentially the productive day today. And if you have no question, then I have to say goodbye to you. And I hope that you enjoy the rest of the day. And I should say see you all tomorrow then, if you have no question. No questions, guys?
Nope.
No?
No question.
Awesome. Then have a nice day, guys. Goodbye, and see you all tomorrow.
Bye.
Yeah. Bye.
Goodbye, everyone.
See you.
See you later. Bye-bye.
Bye, teacher.
Bye, Linda. Take care. Bye, Brian. Have a nice day, Brian.